Okay, my math peeps. Now we do the chain rule part 2. Now, anytime we do part 2 of anything, usually we're adding a layer of complexity to things. So the purpose of this note is we are going to add a layer of complexity, but we're also at the same time going to mention another strategy that we can use as well. And that strategy is called U substitution. So I want to start with that, and then we'll kind of add in our layer of complexity. So another way to approach the chain rule or any other complicated function is to perform a substitution and then make the function simpler to work with. Let's try a substitution on a problem we already know the answer to. Okay, so what we're going to do is we're going to take a look at this guy here. We're going to try and solve y equals y equals x minus 1 all squared. Now, we already know that the derivative of y equals x minus 1 all squared is 2 times x minus 1. Okay, we've been dealing with the chain rule from the previous lesson. That should feel very, very comfortable that this is the answer we should get. Okay, here's essentially what we would do with a u substitution. We let the inside function equal u. Okay, so if u is x minus 1, that's the inside function, okay? And then y will become u squared because I'm replacing my x minus 1 with u, okay? Okay, so then we look at, well, what's the derivative of u with respect to x? Well, that's the derivative of x minus 1, and that would be 1. What's the derivative of y with respect to u? Well, that would be the derivative of u squared, which would be 2u. Okay, now here's what we do with this. How could we get the solution out of these two separate parts? Well, remember, I already know what the solution has to be, right? The solution has to be 2 times x minus 1. Well, take a look at this. We end up going and we multiply these guys together. Okay, what ends up happening is the derivative of y with respect to x. When we do a substitution like this, it'll be the derivative of y with respect to u times the derivative of u with respect to y. Okay, so when we do a u substitution like this, the overall derivative, the original derivative, ends up being the two derivatives multiplied together. Okay, so I would end up with the derivative of y with respect to x is 2u times 1. Okay, so I multiplied the 2u times the 1, and then I just put the u back. Okay, so the u was x minus 1, and I get 2 times x minus 1. Now, you may look at that and say, why would we ever do that? Remember, we're starting with a simple guy. Okay, this is actually super helpful when things get really complicated because it kind of allows the question to clear its own head for a second so that it doesn't look too complicated. Okay, so if u is differentiable, is a differentiable function of x and y is a differentiable function of u, then y is a differentiable function of x, and the derivative of y with respect to x will equal the derivative of y with respect to u times the derivative of u with respect to x. Okay. Why is this relationship true? Okay, so now I'm gonna take an even more basic function. Okay, we're going to take the function y equals 15x. Okay, and what I want to do, just to try and help you get a picture of why this happens, why are we multiplying them together, let's look at 15x as 3 times 5x for a second, and then we're going to call u 5x. Okay, so if that's the case, I know that like if I'm calling u 5x, then I know that I could represent y as 3 times u, right? Because it'd be 3 times 5x. And the derivative of that, the derivative of y with respect to u would just be 3. And then u was 5x, and the derivative of that, the derivative of u with respect to x, would be 5. Okay? Well, let's unpack that a little bit. Recall that the derivative of y with respect to u was the instantaneous change of y with respect to u. Okay? I know I haven't used the word instantaneous rate of change in a lesson or two, but that hasn't gone away, right? The derivative is the slope of the tangent lines, and it's also looked at as the instantaneous rate of change. So what does that mean? That means that the derivative of y with respect to u is how fast y is changing with respect to u. Since dy over du, so the derivative of y with respect to u is 3, that means y is changing 3 times as fast as u. Okay. Okay, now let's look at the next guy. The next guy was the derivative of u with respect to x, and that was 5. So this means that u is changing 5 times as fast as x. Okay, so then we just think about these two things together. If y is changing 3 times as fast as u, and u is changing 5 times as fast as x, then that must mean that y is changing 3 times 5, or 15 times as fast as x. Or dy over dx, the derivative of y with respect to x, would have to be 15. Okay, so it's just trying to show you with a very simplified equation why it ends up, when we do this substitution, that we end up multiplying the two derivatives together. Okay. For many of you, this conversation that just happened in the last 45 seconds is not going to click the first time. Okay, I would strongly encourage you to pause, rewind, watch this a couple of times until you can kind of really piece together what's happening. Okay. Remember that this course is not designed that you walk out of here saying, oh yeah, I totally get this. This course is designed that you have to think about it. You have to kind of fight through some of this and really process some of this on your own and have these conversations over and over and over again until your brain starts making the connections we need you to make. Okay. Okay, so let's take a look at it. If y equals 3x minus 4 to the 5, determine dy over dx, so determine the derivative of y with respect to x, by performing a u substitution. So the hint, which I don't even know if I needed to have given you that hint really, I'd want you to see that it's the inside function that we would call u. So we're going to call u 3x minus 4. Okay, so if we call u 3x minus 4, it becomes y equals u to the 5, because I'm calling u 3x minus 4. Well, the derivative of that, the derivative of y with respect to u, would be 5u to the 4. Okay, now let's take a look at u. U is 3x minus 4, the derivative of that, so the derivative of u with respect to x would be 3x. Okay, and so now we know to take the derivative of this, it's going to be the derivative of y with respect to u times the derivative of u with respect to x. So it's 3 times 5u to the 4. Well, that's 15u to the 4, and then I make the substitution back. So I know that u is 3x minus 4, so we end up with 15 times 3x minus 4 to the 4. Okay, now some of you may say, why couldn't I have just used the chain rule like you told me yesterday and gone 5 goes to the front, and then the derivative of the inside function is 3? Totally fine. Okay, this is just another strategy to use, and it's another strategy that I want you to get comfortable with. Okay, so let's take a look at this one. Again, we're getting a little bit more complicated. But again, you probably are going to be comfortable to say, hey, there's u. Okay, and so y is going to be actually the root of u. So we'll call that u to the 1/2. And the derivative of u to the 1/2 would be 1/2 u to the negative 1/2. Okay. Now I need the derivative of u with respect to x. So u is 3x squared minus 2x plus 1. So the derivative of u with respect to x will be 6x minus 2. And so the derivative of this guy is the two derivatives multiplied together. So I have 6x minus 2 all over 2 root u. Now, before you freak out on me as to where that happened, I multiplied. Not that you would freak out at me. I know you won't freak out at me. I multiplied this and this together. Okay. This u to the negative 1/2 is 1 over root u. So this whole thing becomes 1 over 2 root u. So when I multiply these guys together, the 6x minus 2 is on top and the 2 root u is on the bottom. Okay. Then I substitute my u back. So u is 3x squared minus 2x plus 1. And then the only other thing I did here was I simplified it. I essentially like reduced my fraction. So 6x minus 2 over 2, I can divide that and that would become 3x minus 1 over 1. Okay, I just kind of took a 2 out of both of those. Okay. Okay, so here we go for our added level of complexity that I was talking about earlier. Some of you are thinking to yourself, didn't you already just add that level of complexity? Nope, it's now. So let's have some fun. Differentiate g of t equals t squared plus 1 all cubed times 3t minus 2 all to the 4. Leave your answer in factored form. Okay, so overall, what I need you to see here is I've got something times something there, right? And so that's the product rule. So the product rule states, the product rule states the derivative of my function will be the derivative of f times g plus f times the derivative of g. Now inside here though, we're going to have to use the chain rule. So the derivative of f. Okay, so this is f. I just want to underline what we're talking about. There's f. So the derivative of f is going to be 3 times t squared plus 1 to the 2, right? That 3 comes to the front and the degree drops down 1, times the derivative of the inside function, which would be 2t. Okay, times g, which would be 3t minus 2 all to the 4, plus f, so that would be t squared plus 1 all to the 3, times the derivative of g. Now the derivative of g would be 4, right? The 4 will come to the front. 4 times 3t minus 2 all to the 3 times the derivative of that inside function, which would be 3. Okay, so that is what I just said. Yay. Okay, now let's just clean this up a wee bit. I can take 2t and the 3. We'll multiply those guys together. So that'll be 6t. Sorry, I'm just trying to get my ink back on. So that'll be 6t. And then I can take the 4 and the 3 and make a 12 there. Okay, so that was just me cleaning things up. Now, I want to take a look at this and say we want to factor out what's common. Okay, so take a look at this. I've got a 3t minus 2 to the 4, and I've got a 3t minus 2 to the 3. That means 3t minus 2 to the 3 is common to both of those. So I'm going to factor out a 3t minus 2 to the 3. I've got a t squared plus 1 squared and a t squared plus 1 cubed. That means the squared version is common to both, so I can factor that out. And then I also have a 6t with a 12, so I can factor out a 2. Okay. So I'm going to do all of that. And sorry, I said factor out a 2. I meant factor out a 6. Really, I did. So I factored out the 6. I factored out the t squared plus 1 squared. Then I factored out the 3t minus 2 cubed. Now, what am I left with when I factor all of that out? Well, when I look at this first guy, when I factor out the 6, I'm left with a t. I'm left with a 3t minus 2. And then I don't have the t squared plus 1 because the whole thing came out. Okay, when I look at the second guy, 12 divided by 6 leaves me with that 2. I have 1 t squared plus 1 left, and I don't have the 3t minus 2 cubed because I factored it out. Okay, so now I just want to work inside here and just clean this up, okay? I can leave this as the 3 factors. I don't have to do anything with that because the question said leave it in factored form, okay? Now, I don't actually need these brackets here anymore once I've, because I just put those brackets there to show you what I was taking out, okay? But it's just something times something times something. So those square brackets on the first half there aren't actually needed. T times 3t, t times -2, 2 times t squared, and 2 times 2. is the next thing I will do there. Okay, and so that leaves me with 3t squared minus 2t plus 2t squared plus 2, combine like terms. And so my final answer would be, again, I just dropped those square brackets from the front guy. So 6 t squared plus 1 squared times 3t minus 2 cubed. And then combining like terms there, I got 5t squared minus 2t plus 2. Okay, so this would be my final answer. That would be the derivative. Isn't that fun? Oh, so fun. Okay, let's do another one. So determine the derivative of x squared times the root of 1 minus x squared. Now, again, I'm going to look at this from the perspective or the lens of the product rule. I'm just going to write this as an exponent first. So I'm thinking in my head, okay, I'm looking at the derivative of x squared times 1 minus x squared all to the 1/2. Okay, so again, this is the product rule. I'm looking at the derivative of f. Sorry, I just realized I was probably hiding that. Let me just, I'll make myself go away for a second. That's what I was talking about here. Okay, I just wrote it as exponent of 1/2 instead of the root. Okay. Okay, sorry about that. Okay, so I'm using the product rule. And I've got the derivative of f. Well, the derivative of f is 2x. So that's 2x times 1 minus x squared to the 1/2 plus f, which is x squared, times the derivative of g. Now, the derivative of g will be, that's the chain rule. So 1/2 comes to the front times 1 minus x squared to the negative 1/2 times the derivative of the inside function, and the inside function derivative there would be negative 2x. Sorry, negative 2x. Okay. All right, so now we want to work on cleaning this up a little bit. So over here, I can multiply my negative 2x with my x squared. So that'll be negative 2x cubed times 1/2 as well. So then that'll just be x cubed. Okay. So now I'm looking at 2x times 1 minus x squared to the 1/2 minus x cubed times 1 minus x squared to the negative 1/2. So now what I want to do is I want to factor out the 1 minus x squared to the negative 1/2. I can also factor out 1x. So when I take the x out of the first guy, I'm left with 2 times, and then when I take the 1 minus x squared to the negative 1/2 out, I'll be left with 1 minus x squared. Again, if that's confusing you, remember when we are taking it out, we're dividing it, right? And so you want to think about the fact that you're going 1/2 minus negative 1/2, essentially, because when you divide powers of the same base, you subtract the exponents, and 1/2 minus negative 1/2 is just 1. Okay, and then on the other side, when I have taken out the greatest common factor here, I took out that x, so that left me with x squared, and then I took out that whole thing, so he's gone from there. Okay, so now I can distribute that, so that's 2 minus 2x squared minus x squared. So altogether, that's going to be negative 3x squared plus 2. And then this guy here, I can move to the bottom because he's a negative exponent. Okay. And so that leaves me with this guy. So 2 times, or x times 2 minus 3x squared. I had said negative 3x squared plus 2, same thing. And then this guy moved to the bottom. So that's how I have the root of 1 minus x squared on the bottom. Okay. All right, good. Let's do another one. Okay, so differentiate h of x equals 3x minus 1 all over x squared plus 3 all to the 4. Now, again, what I want you to see here is, first of all, the chain rule that 4 would come to the front, okay? And then this would drop to a 3. But then I have to take the derivative of the inside function. And taking the derivative of the inside function is actually using the quotient rule that we did a couple of days ago. Okay, so the quotient rule, I'll just hide myself here for a second, was this. So it's the derivative of f times g minus f times the derivative of g all over g squared. Okay. All right, so here we go. Here's the first thing we're going to look at. So again, I'm doing the chain rule. The 4 came to the front. What I had dropped a degree. And now I need to take the derivative of the inside function. And the derivative of the inside function was the derivative of f. So 3x minus 1, the derivative of that guy is 3 times g, x squared plus 3, minus f, 3x minus 1, times the derivative of g, which was 2x, all over g squared, which is x squared plus 3, all squared. Okay. Now, we are going to work on cleaning this up just a wee bit. Okay, so my 3 can get distributed here and my 2x can get distributed there. So that's going to give me 3x squared plus 9. And then there's a subtraction sign there too. So I counted that as a negative 2x, so negative 6x squared plus 2x. Okay, and then when I combine like terms, I would end up with negative 3x squared plus 2x plus 9. And then remember, we've talked earlier that our answer should always be one nice pretty fraction. So essentially, this is like, I'm just trying to get my ink back on. This is like 4 over 1, right? So I've got 3 items on the top that are being multiplied together, and then these 2 items on the bottom. Just remember that that exponent of 3, if you're going to do that, applies to both. So this is an exponent of 3 on the x squared plus 3. So x squared plus 3 to the 3 times x squared plus 3 to the 2 is going to give me x squared plus 3 to the 5 as my denominator. Okay, and so kind of the simplified version of this ends up being the top multiplied together, so 4 times 3x minus 1 cubed times the negative 3x squared plus 2x plus 9, and then on the bottom, I get my x squared plus 3 all to the 5. Okay, so you can imagine that the homework around here, you want to take your time on, okay? One small error and the whole thing kind of falls apart. So take your time and make sure you're really focused on seeing everything that you have to do. Really, there's nothing new in today's lesson, right? It's just adding a bunch of pieces together, and you just got to be careful that you see all of those pieces. So determine the derivative of y if y equals the root of x plus the root of x squared plus 1. Okay. All right. So again, I'm going to hide myself for a second so you can see what I put there. But first thing I'm going to do is look at this from the perspective of that overall big root is the same as saying to the power of 1/2. Okay. Now what I see is I first see the chain rule. So this is going to come to the front, and then that will drop to a negative 1/2. But then I'm going to have to take the derivative of the inside function. When I go to take the derivative of the inside function, well, that's 1, but then this is another chain rule. So this will come to the front. This will become negative 1/2. And then I have to take the derivative of that inside function, which is 2x. Okay. I know I hid myself at the moment, so you can't see my smirk on my face as I go through that, but here we go. Okay. So that's what I'm going to do right here. So I have gone 1/2 times my original function to the negative 1/2. Now I have to take the derivative of the inside function. Okay, so the inside function is this guy right here. So that's going to be the derivative of x is 1. That's where this one here comes from. Now I have another chain rule. So that 1/2 comes to the front. So I have 1/2 x plus 1 to the negative 1/2 times the derivative of that inside function, which is 2x. Okay, now I have to work on cleaning this up. And then the other thing I did here was I took my x squared plus 1 to the negative 1/2, and I brought it underneath, okay, and called it a root. Now, the next thing to do, it's just so that you're all with me, I also called this guy a root as well. That's where that one came from, okay? The next thing to do, I can see that these 2's will simplify out on that fraction. They'll divide each other out. And probably I want that as one fraction. So I'm going to look at my 1, and I'm going to call my 1 the root of x squared plus 1 over the root of x squared plus 1. Okay. So that's all I've done there. Now I have a common denominator. So this ends up being x plus the root of x squared plus 1 all over the root of x squared plus 1. Okay, which I'm going to show you in 1 second. I'm just going to have to switch slides to show you. Okay, so that's where my x plus root of x plus 1 came from. But now, the other thing I did was I said it was to the exponent of 1. Now, the exponent of 1 is nothing, right? I haven't changed anything, but the reason I did that, and then I also made it a different color, I made it pink, because I want you to see overall, like everything happening here is multiplication, right? So when I now look at these pink guys, these are powers of the same base. Okay, and when I have powers, when I'm multiplying powers of the same base, I can just add the exponents together. So I can actually make that become one item now by just adding the exponents. So negative a half plus 1 will give me positive a half. Okay, and so that's where that positive a half came from. And then my 1/2, what that was in front, that 2 just ends up on the bottom there. And then this guy was also on the bottom, so he ends up there. Okay. Now, the only other thing I'm going to do is I'm now going to put my roots back. And so I end up with that 1/2 became the root of x plus the root of x squared plus 1 all over 2 times the root of x squared plus 1. Okay. And then that would be the simplest version that I would answer in. Okay. All right, I know your head's probably spinning a little bit, and that's good, right? It's good to have your head spin because that means your brain is trying to make some connections, and they're gonna come, but you need to practice lots and lots and lots and lots, okay? All right, so here's what you're doing, and take your time and connect with me if you have any questions, okay? All right, implicit differentiation is next, so I will see you there. Take care.